Living Room Logic. Welcome to Living Room Logic and part 2 of Einstein's quantum conundrums. This episode was so good that we had to break it into 2 episodes. There was just so much there. So sit back and enjoy some more.
I think a big reason I like biology is because it's also relatable.
Yeah.
And this stuff is so abstract that it's much more difficult. But with that in mind, let I remind everybody that I'm about to discuss quantum mechanics and all of that, and how the mathematical principles just don't match. And you know, I'm going to be a damn good host explaining this. I promise. I promise that you won't waste your time, whether you're entertained or interested. You'll either, because either one way or another, you'll have something coming out of it.
You'll either have a headache or you'll feel good.
I swear, you need to turn this episode into a drinking game if you're a physicist and just go for it. I love it.
Something wrong.
Oh, well, you don't want to kill them. But you know, at the same time, look. Okay. So we're gonna spin the wheel of time back, right? So Aidan just gave a really intriguing outline and history and everything about particle physics. You know, the discovery and the understanding of what's going on about all of these different particles. But I'm gonna talk about the mechanics of them, right? So when we say mechanics refers to how Aidan's so happy to have his turn done. Oh, he's delighted. When we say mechanics, we're talking about how we calculate movement, how we calculate momentum, how we calculate the amount of energy needed to move a box from A to B. And we understand that. We've observed it, we've measured it, we've tested it, we have it, okay? Done and dusted, easy to do.
Class.
Yeah. Then you get to the teeniest, tiniest scale and it kind of falls apart. Okay? So I want to break this down, right? So quantum mechanics. Quantum, okay? We hear quantum, and to be honest, most of us probably just go to the movies and stuff, and like we go to a mad end of the world movie and they're like, the quantum nuclear accelerating biomass is going to save us, and it makes absolutely no sense. You hear the word quantum and it makes no sense. Quantum is because as we went looking smaller and smaller and smaller, we were in search of the original quanta, the one, the like, what is the absolute subunit? So quantum mechanics is the minimum, the smallest amount, the same thing that those Greeks were talking about, the smallest amount of anything. And a physicist called Max Planck actually was like, oh yeah, I got it, yeah, sound. And he was like, I figured that one out, I got it. And he found the smallest amount of energy possible in the universe. Okay? All energy in existence is divisible by this amount. It's a certain number of this amount of energy. Maybe it's like 50 billion of this Planck amount of energy, or it's just a couple hundred of this Planck amount of energy, but you cannot have less, and you cannot have halfway between 1 and 2 Planck amount of energy. Okay? So there is a lowest number subunit, right? There's also a smallest length. Okay? So the smallest distance between 2 points is defined. Okay, so in the same way that, let's say you have 1 centimeter, 2 centimeter, 3 centimeter, you can have 1 Planck length, 2 Planck length, 3 Planck length, but you cannot have 1.5, 2.5. That does not exist. This is the minimum. And quantum mechanics is talking about how we have all of these smallest amounts of things, and when we try to apply the same calculations that we had already, things kind of hit the fan. And it doesn't work anymore. So they had to develop an entire new layer of physics to understand it. Because if I throw a rock at Aidan, he gets hit by a rock.
Sure
but in
do.
quantum mechanics, sometimes I get hit by the rock. And that doesn't make much sense because I threw the rock at him. Okay, and let's just presume, let's take the like fundamental thing of I can hit him with a rock. If I aim for him, I hit him. Sometimes I hit him, sometimes I don't. So that kind of
You're saying at the quantum scale?
At the quantum scale, yeah. Okay, but what I'm trying to say is that things are very definitive at the big world scale. If I try to hit you with a rock, I'm going to hit you with a rock. Okay? I got you. I got that. But at a quantum scale, it's less certain. Okay? We're not entirely sure.
Even at the scale like that I was talking about, at the scale of kind of subatomic particles.
Especially.
Yeah. So that's when it starts getting crazy and weird.
Really weird, really spooky, right? And let me just so basically Max Planck came out with this and everyone was like, oh bruh, that is weird. Okay, that is some funky stuff, and it's crucial. It's the Planck equations, the Planck constants are crucial to our understanding of teeny tiny things. In 1905, it's so crucial, right, that in 1905 Einstein looked at this and was like, that's pretty interesting. And he developed his first major finding as a scientist, where he took that math and was like, that means light is probably something. Okay, you know, light is probably made up of something because it has to come from this. And he theorized the idea of a photon before it was discovered. He was like, photons must exist. That makes sense. And the reason he came up with this, right, which I think is really cool, is those... Back in the day, there was something called the photoelectric effect, right? Where you had a sheet of metal and you would shoot light at it. And every now and then you would shoot it with enough light that an electron would pop out. If you go into it the presumption that light is energy, and that this energy is not constant, so sometimes you can have high energy and sometimes you can have low energy, it means there has to be something mediating this energy increase, right? So he was like, okay, so we have photons. Photons are the, subunit, the particle thingy of light, and if I shoot enough photons at this metal plate enough times, it will eventually work. And then he kept shooting photons at this metal plate, and he was like, why isn't this working? And he found that it wasn't the amount of photons, but it was the frequency of photons that made a difference. So it wasn't that if you shot 1 million photons at a sheet of metal over 1 million years, it wouldn't do much. But if you shot 1 million photons at it in a second, the metal plate didn't like that. Okay. So what he was saying was that it was acting as a frequency.
Yeah.
And from this, he was kind of like, well, frequencies are more so related to waves, wavelengths and all of that stuff. And he was like, that's freaking weird. How does that work? Because wavelengths are the kind of things like your microwave works at a wavelength. You're trying to get the radio working in your car. You're looking for the right wavelength. That's stuff that travels through the air. That's not particles. That's not, because, you think of a planet and you understand a planet. So our whole idea of particles and all of that is that there is a structure which has some mass. And Einstein went, oh, well, shoot, a photon, it is a particle, but it's also a wave. And with that discovery, it totally messed up everything. Everything. From all of classical physics was like, what, mate? And the interesting thing about this, right, is that Einstein was desperate for a unifying theory. That was his life's goal. He came up with the whole E equals MC squared shindig, which was just, he figured out all mass was just a form of energy. All energy could be converted into mass. And that's really cool. And he wanted to find the unifying theory, like Aidan mentioned. But this kind of messed it up, because he was using classical physics to try and understand everything. And then we had these two things that didn't match. And that screwed him up a bit, okay? And it screwed him up for a few reasons I'll get into right now. So there's this thing that people who watched Breaking Bad might have heard of, called the Heisenberg uncertainty principle, right? In Breaking Bad, your man goes wild and he calls himself Heisenberg because he was a chemistry teacher. And this is the guy who inspired him, okay? So be careful, choose your heroes carefully. But... Okay, so when we look at quantum mechanics, things don't act normally. Okay, if I throw a rock at Aiden, like I said before, 50% shot of hitting him, because sometimes it doesn't do what you want. The uncertainty principle, right, is saying that if I measure how fast a particle is going, or anything like that, I have no idea where it is. I can just measure where it's moving and how fast it's moving. But if I measure where it is, I have no idea how fast it's moving. I can't know both. I can't both know its speed and its position.
Yeah.
And that created the uncertainty principle. And people use this uncertainty principle to kind of be like, basically to talk all sorts of nonsense. But the basic idea is that since it's a wave, it acts differently. It behaves differently. And the best way to compare this is to compare it to a plane and how radar systems detect where planes are and how fast they're going. Let's say I shoot a beam of some laser that will hit the plane and come back to me. If I hit a single, one little short, super short beam, it will go ba-boing and come back to me. And I can figure out, based on the speed of light, how far away it is. Okay? I have no idea how fast it's going. I have no idea how fast it's going. I'm only taking a short read of it, and it's saying, right, it's this far away. But if I, instead of that, go, I'm going to shoot for 3 seconds, waves as it. So it's like, whoa, 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 hits the plane, whoa, 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 comes back. I can tell by the change in the waves on the rate at which it comes back how fast the plane is going, right? But I'm not as certain about where the plane is. It could be in any of the positions from which I measured its movement. I don't know which direction it's going. I can't know exactly where it is, but I know how fast it's going. And that's what Heisenberg's uncertainty principle comes down to. It's that if you record something for a long time, you know how fast it's booping about. If it's going boop, 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 flying around the atom per se, you can know how quick it's going. But if you take a short snapshot, you can't know how quick it's going, but you know where it is. Yeah. And that's kind of where the Heisenberg uncertainty principle comes to, and which is, and it is complicated because the basic fundamentals of how we've tried to understand everything was having both pieces of information all of the time, which we can't quite do
at the quantum level.
At the quantum level, because the line certainly blurs. And this is like very much so used to look at electrons, which are called particles, but they're both. It's the same as a photon. They're kind of both.
That to do with electrons. I was like, is that sounds exactly like what we're taught in kind of Leavenscert chemistry about electrons, that it's like a...
And it's wrong. It is wrong, says the biologist who's nervously waiting for angry emails. But it is wrong. The electron isn't a particle per se. It's more of a cloudy wave around the atom. It's more of a cloud. You can say that some will exist here, some will exist here. This is just where they're cozy. But it's very, very complicated, right? And a lot of these particles, like the electron, like the photon, they behave as waves.
Yeah.
And back to Aidan's point, when you're trying to look for these particles that behave like waves, it can be really confusing. Because since you're constantly getting all of this noise, think of any wave, okay? Just think of a sound wave, or think of people throwing rocks into a lake. If I throw a rock into a lake and you're trying to pick out which ripple is coming from the God particle rock being thrown into a wave, how the hell are you meant to differentiate between all of the different ripples being chucked in all the time? And that gets really complicated. And it messes everything up, right? It's like looking for a violin in an orchestra and all you have is the audio data. You can't even listen to it. You're just looking at the numbers going, I understand this because I'm a biologist. And I'm sure that there are people who do understand it. But I'm not one of them, okay? And I am aware that there's something called the Fourier transform, which is, in my opinion, not possible to explain comfortably by myself or over a audio thing, because you kind of need to visualize it, and I encourage people to go check it out, the Fourier transform videos. There's a few people who do it really well. But it is possible to actually filter out the noise, which is really cool.
Okay.
So this whole thing, right, and going back to Einstein was completely displeased. Because Einstein was like a teacher with his least favourite student getting a top grade. He really wanted to dock marks, but he couldn't quite find a mistake. He was super not happy. Even though he made a big discovery with this, it still contradicted everything he wanted.
Yeah.
So himself and a lad called Niels Bohr got into a debate where Einstein said, the laws of physics are completely objective. It doesn't matter where I am, what I am doing. Who cares what I am doing? It doesn't matter. The laws of physics are objective. They will exist. Whilst Niels Bohr said, actually, they're quite subjective. Because when I try to measure something, it changes things. If I try to measure the speed, like the uncertainty principle, I can't know the location. It's a bit of a 50-50 split. It's not always in the same place. Yeah. Things are relatively random. There's a probability to them. And Einstein's whole shindig was special relativity. He was all about like locality. He was all about, I'm here, the sun is there, there's all of these gravity things going on. And, you know, he was like, there are set laws. And Bohr was basically saying, nah, fam, I disagree. So they came up with an experiment, right, with the help of, remember you mentioned the Irish lad, John Bell. John Bell, you know, probably a name that should be in more households in Ireland especially. He came up with an idea, and I'm going to super simplify it and then relatively unsimplify it, okay? Relatively. Wahey. Okay. When we talk about the transfer of anything or the movement of anything, the top speed is the speed of light, correct?
As far as I'm concerned as a biologist.
Yes, so as far as you're concerned, like nothing in the universe can go faster than the speed of light. That's Einstein's whole shindig. That's everything. That's the passage of information. That's the passage of all this stuff.
That's the speed at which photons and gluons travel.
Yeah. Let's say I do a balls and cup in front of you. You know when you put like multiple balls underneath cups and I move them around in front of you and you don't know which is which? Right. Underneath these cups, I showed you beforehand that one is blue and the other one is red. And I shuffled them up until you were like, I'm completely clueless. I've left the room multiple times. You've been here for hours. Leave my house. And you're sure that you don't know which one is which. Okay, yeah. You take one cup and lock it up and you don't look at it. And I take the other cup and say, Elon Musk, I have a cool idea. Can you please shoot this at least 2.5 light years away? The idea that John Bell came up with, and this was entirely John Bell's idea, was that the second you look under one cup, you know the colour that was under the other cup. So you know the information that is 2.5 light years away instantaneously. So you know exactly how that exists faster than the speed of light. Something which is 2.5 light years of the speed of light away from you, you can say that's a red ball because you opened up the cup, it was a blue ball. You're like, the other one's a red ball. So this basic thing messed up Einstein's thing because he was like, right, but that's faster than the speed of light. We can't have that conflict of the passage of information. We can't instantaneously know something that far away. And which has now kind of been shown more recently to be like, well, it's not the passage of information can be that quick, but the verification cannot. That is the problem. You cannot verify faster than the speed of light, but you can know. So that's, yeah. And so Einstein himself called this idea spooky. He called this spooky physics.
Dude, this is spooky.
He said, so I'll say that exact experiment, but with physics talk, right? God help me. So what John Bell said, when you split a pi meson. Remember all of the funny named things that Aidan mentioned? There's one called a pi meson. Sounds delicious. Okay. When you split it, it turns into a positron and an electron. And these positrons and electrons, one has a negative charge, the electron, and one has a positive charge. So we can do exactly this. And the measurement of one will tell you the charge of the other. Same experiment, okay? You could send one positron, collect it, and don't observe the data, and then send the electron until it's very, very far away. And this is completely random. You immediately know, once you analyze one of them, you know the charge of the other. And this has been proven lots and lots of times, okay? But even more so than this, we have a completely still meson, correct? Okay, let's say we have a perfectly still pi meson. When we split it, we create two spinning objects. One spinning clockwise and one spinning anti-clockwise, because they came from an object with no spin. So momentum and spinning has to be conserved. They have to cancel each other out. Okay?
That makes sense.
When we split them, again, no matter what orientation we observe the spinning, we are 100% certain that the other electron or positron will have the opposite spin, because angular momentum must be conserved. The spinning must be conserved. It doesn't matter what way you look at it. If you try to look at it from the side, from the top, upside down, there's different probabilities of getting it clockwise or at an angle or anything like that, but you always know that the positron spin and the electron spin will go at different directions, always. And that's really messed up, because that's when Einstein came then out with the quote that people have heard, where Einstein said, God doesn't play dice. Because you're not meant to know that. You're not meant to be able to say, okay, well, this one is spinning, anti-clockwise at this angle, and then you immediately know
what the other one is
what the other one is doing. And that's the idea of entanglement, okay, where these two things came from the same origin and they must balance each other out. And you might hear things like quantum computing, and the whole idea behind quantum computing, right, is that when, do you ever see hackers in these movies like The Matrix, where they're like click, 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 and it's like The Matrix, and you just see zeros and ones flying down. Well, at its nuts and bolts, the computer language is just zeros and ones. But it's still held back by the speed of light, because it's passing information through electricity and fiber optics, all that shenanigans. Yeah. But quantum computing skips that step. If I make a particle spin clockwise and you receive it on the other side as, it's going anti-clockwise, you're passing information instantaneously. Only as fast as you can perceive it. And that's completely crazy.
That's amazing.
I think that's bamboozling.
So it's just a way to speed up computing even more.
Yeah. But Einstein, right, he hated it until the day he died, because Einstein said there has to be something that connects it, and John Bell completely disproved it. Einstein said we need to put this all together and make it cohesive. There's obviously things that we haven't learned yet that make sense of all of this. And this experiment by John Bell completely disproved it. He was like, no, he got rid of the need for any constants, because no matter what way you did it, it always worked out. There was no predetermined thing that it will always spin this way or it will always spin that way. No matter what way you look at it, no matter what way you measure spin or anything like that, you will always get the opposite result in the other particle.
You're a goddamn genius.
Yeah, so John Bell, what a man.
This guy, John Bell.
Yeah, God bless him. And so we talked a lot of nonsense there. And to continue that, I want to talk.
Einstein's sad. And it makes me feel terrible, but the fact that John Bell's like, fuck you.
To be fair, they were slightly different ages because John Bell said this in the 1960s.
And that's when Einstein was probably very old.
Old or dead. I don't know his exact lifespan, but like Einstein did most of his discoveries between 1905. I was about to say 05 and 12, and I was he left
1905 Europe to America before the Second World War, so maybe the 50s and the 60s he died.
Yeah, something like that. I don't have it in front of me, but John Bell basically brought together this, because you're a brave man to go against Einstein. Back then he was kind of he must have been drinking his Baileys that day. But
I know you are.
But like, I am. I'm red in the face, and I'm just trying to have a good time as I talk absolute wild stuff. Okay, but I want to talk about one more thing, which is cuckoo crazy birds. But some people believe it, so we'll go into it. Okay, so there's this idea of the many worlds interpretation, right? And this is kind of talking about like your parallel universes, all of this stuff. Mm-hmm. And this basically says, let's say I'm about to read one of these particles. I don't know if it's a positron. I don't know what way it's spinning. I don't know what's going on. But I say, if this is an electron spinning clockwise, I'm going to walk left and keep going. Mm-hmm. And if it's not, I'm going to walk right. The many worlds interpretation says that since this is a probability-based thing, since you don't know which one will happen, you can't know, that it means that either can happen. And once you observe it, once you subjectively measure it, you develop a multiverse, and you are in one, and the other person is in the other. So one person actually found the clockwise spinning electron, kept walking left and got hit by a bus, and the other person didn't find it and kept walking right and found the love of their life. And these exist in two separate universes. Mm-hmm. That each of these quantum bunny-eared probability decisions create their own timeline, which is, in my opinion, cuckoo crazy birds. But there are a significant amount of people who really believe this. And like many things in life, I probably just don't understand it.
Yeah, it's not belief. Like, these things sound crazy, but they have an extreme amount of mathematical and theoretical evidence behind them. Now, experimental, I don't think it's possible.
Yeah. Well, the many worlds interpretation, I have no idea if there's maths behind that. I just know that it's an idea that's floating around that a lot of people like to talk about.
Okay.
I don't know if there's maths around it, and even if there was maths around it, I couldn't exactly look at it and give you a good idea of if it was correct or not. I would just go, well, this guy wrote about it, and I'm telling you what he said in the discussion, not in the actual calculations part, because I don't know. I can't check that. I can't check that stuff. I don't understand how to check proofs. Anyways, to continue my beautiful rant about things I completely don't understand, let's talk about string theory, which
is about my shoelaces.
Which is about Aiden's shoelaces, right? And how Aiden's shoelaces, when you tie them together, he both falls over and answers all of the darkest questions of the entirety of the universe, all in one brief swoop. Okay. So, string theory, right? It says that when you go down past all of these elementary particles that we've talked about, we end up looking at these rings, these circular strings, right? And the idea is that depending on the frequency that these strings vibrate at, we get different particles. Just like you'd get different notes on a guitar. If it was vibrating at one way, you'd get an electron. Another way, a quark. Another way, a boson. All these different strings coming together to develop all these different particles. Okay. And string theory is actually the maths that works that says it brings everything together. It brings classical mechanics together. It brings gravity together. It brings all of the different forces together. And it perfectly works. It is a unifying theory.
Well, happy God.
If the universe existed in 10 dimensions. Which
we don't have those.
We don't have those. So string theory is like, it's like cavemen having a Ferrari and trying to reverse engineer it to something that they can work with, because they don't even have petrol. They can't use the Ferrari. They don't know what's going on. Mm-hmm. So they have to do it.
Red and shiny.
Yeah, exactly. They use it for cover from evil rain. But seriously, like that, and string theory in a big way is like that, because the thing is that there was a scientist, I don't know his name off the top of my head, probably because I'm drinking Baileys, but he took the 3 dimensions of space that we have, and he was like, I want to see how math works out at 4 dimensions of space. Mm-hmm. Okay? Mm-hmm. And when he did that, almost by accident, he couldn't do it. All of Planck's equations had to be put in, and the whole universe kind of clicked together, you know? So all these formulas that we had were completely necessary to make it work in 4 dimensions. Mm-hmm. And then you go 5, 6, 7, 8, 9, and 10, and at 10, everything's a bit different, but it all works really well. Like, you have everything, quantum mechanics, classical mechanics comes together. You can predict everything. You can make sense of everything. It's a unifying theory. Einstein is somewhere drinking his own Baileys in heaven somewhere, if he believed in that, saying, I told you so, in his 10-dimensional heaven. But we don't live in a 10-dimensional universe. We live in a 3-dimensional space with a 4th dimension of time. And what they really are trying to reverse engineer it to say, well, it can exist in a different way, but not a way we can understand, because even these strings on the plane of 10 dimensions, these strings are 2-dimensional. So they don't even have volume. It's crazy. Like, for me, it's too abstract to have a clue what's going on. But I felt like it was also, at the same time, far too important for me to just completely ignore when we were discussing quantum mechanics. Because string theory is basically the minimum quanta. It is saying that there is a minimum, the smallest thing is that everything is made out of these strings, and depending on how they vibrate, all of existence comes into being. You cannot have string theory without a string that produces gravity. It jumps out at you. You need to put it in. Mm-hmm. You cannot have it without producing electromagnetism, all that stuff.
The only thing I can say about string theory, and nothing to do with my shoelaces, is that
that's shit.
I was listening, I forget the name of it, Science Information Weekly, I think it's what it's called.
Okay.
And they were saying that if you were to build a Hadron collider that could create enough energy to kind of detect some of these particles, or to detect shifts or ripples in a field like the string theory field, that you would need to build a collider the size of the Milky Way galaxy.
So, not in our lifetime, but it's a cool concept. All you physicists, you guys are crazy. That's a wild one.
What is amazing is that there's something beautiful about theoretical physics, in that they can just go off on these crazy ideas.
Absolutely.
And they can go, well, how would you experimentally test this? Well, you'd have to build something the circumference of the Milky Way galaxy.
Like, there's a lot less ethics involved. Poor biologists. You can't have any wacky, crazy biologists. they'd say awful things. Like, how do you, like, oh, I don't even want to give an example because the only examples would be terrible. But like, you can't have wacky biologists. We're too tied in by ethics. We're working with living things. But physicists, you guys go wild. You do it on our behalf, you know. Go for it, guys.
Yeah.
Keep talking about your funny strings. They're so cute.
Well, you know, the idea is that the next collider will be it'll be at the same place in CERN. It's going to be like 100 kilometers. So, and there's this perfect part of the Geneva Basin that like they can see it fitting in. And
oh my God.
The cool thing is that the one before, like the Large Hadron Collider actually is fueled or like is pumped by a smaller particle accelerator that was built say 20 years before, and it's 7 kilometers in size.
Oh my God.
Small positron super collider, something like that. I probably butchered that, but and then it's feeding. It's like a tiny ring, and it's overlapping the bigger ring. And then you want this bigger ring to overlap the tiny ring that's filled in with the middle ring.
Oh my God.
And it just goes on, I guess, until you
That's
make
amazing.
one the size of the Milky Way galaxy, and you finally we've got these Dyson spheres chucking out energy, and we're just like, everyone is just building this feckin' Hadron Collider that is sending these dudes, these protons, you know, yeeting around the Milky Way galaxy.
Just one particularly convincing physicist who's like, no, we need to know about like elementary particle number 164, because if we don't learn about that one, how will we ever prove string theory? Okay, I know we have like 900 to go, but we need 164 next. It's all about the steps.
It's all about
the steps.
But the crazy thing is, and it's actually something like to do with particle physics that I don't really understand, or not that I don't understand, but that...
Oh, this is the part you don't understand. Okay, well, I'm glad we got
that
there.
I don't understand the most.
Oh, okay.
But if you think about it, like, I've been listening in to what's going on with the LHC, with the Large Hadron Collider that is, you know, that found the Higgs boson. And that's really the only kind of major particle that they've found. And it's kind of like, how are they going to be able to build a bigger one? How are they going to... Is it possible for them to find that the human backing, because that was such a huge project?
Yeah.
And it's like, are they going to be able to get enough people to back this next bit and be like, that was key, and now we need to scale up again?
I think it's like I suppose then again we're looking at it from like in biology. There's just so many biologists with so many ideas that it's hard to get funding. But like, it's pretty good to be a very rich person who says they helped pay for that, because it's notoriety as well. So they probably will be able to get the money for it just for the sheer notoriety of it. You know, you could be the person who funded the foundations of the next particle. And like, I suppose that's something that probably should have been mentioned, was that the vast majority of these particles, like we had the like proton, neutron, electron, all of that was quite early, but it wasn't like, it was like between the 50s and end of the 60s that the vast majority were found. And there was maybe like 3 or 4 in the 70s, 2 or 3 in the 80s, 1 in the 90s, 1 in the 2000s even, and then the
2012
2012 the Higgs boson. So, you know, all parts of science eventually become quite incremental. Once you stop getting we've understood, or at least detected, the vast majority of it, and now it's quite incremental, and it becomes more and more difficult to find these things.
I don't know. I might challenge you there, Andrew, because I think that I know what you mean, that you're saying that it's slowing down, and that like it's as a biologist, the way that I can analogize it is, if you're looking through a sample for species
Yeah.
of tiny things, that you find
Yes.
loads of them at the start, and then you look through the whole bloody thing of the sample to try and find those last few rare species, right? And it takes you
Yeah.
ages. And so this is what they're doing, but I think maybe what is happening right now is with this standard model in its current form, it still doesn't work.
Yes.
And you said it yourself, gravity is not incorporated into this. And so
Yes.
there needs to be a better idea or a better theory that can incorporate gravity into the kind of this electro weak theory, you know?
Well, I don't disagree with that at all. I don't disagree with that. I just think that the era of science in which we're getting a major discovery every other day is kind of gone. Is what I'm saying.
Yeah.
Is that you could build this XXL Hadron Collider, and then you could find the next particle, and that discovery will move science forwards quite a lot. It'll have like a exponential growing effect.
Mm-hmm.
But we've discovered a lot, you know, and it's the same in every field of science. There's a lot discovered, but now we're just fine-tuning the kinks that are left.
Mm-hmm.
For everyday existence, Aidan, does it really matter if we completely understand quantum mechanics?
Yeah, it doesn't. It doesn't, but
Like, you know, it doesn't matter yet. Like, I imagine once things like quantum computing and the death of the universe become quite important, it's probably going to be quite vital. But it's not like that, and it is the same in all of them. Anyways, I had a great time. My Bailey's is gone, nearly, and you know, that was enjoyable, Aidan. Did you have a good time?
I had a great time.
This is the end of the podcast. We hope that you enjoyed your time. If you're feeling generous and you're not completely skint like us, why don't you give us some of your money? Join our Patreon. Join our Patreon. Join our Patreon. Join our Patreon.